So finally, we are at the point where we can compute cellular homology in some concrete examples. And the degree 1, so the cellular chain differential from degree 1 to degree 0, is something I want to have a close look before we really start with the examples. So the typical push out that we have to look at in degree 1 looks like that. Attaching maps that start from S0s, copies of S0s, to the zero skeleton. And we attach 1 cells. I think we write the skeleton like that, right?
Yeah.
Always forget. So let's say this is the push out for the 1 skeleton, and then the incidence number has a very concrete meaning. So the incidence number in that situation is either 1, -1, or 0. So the J, we have the 0 skeleton is just a bunch of points. Might index them with J. And the incidence number for the cells, the 1 cell I and the 0 cell J is 1 if the attaching map, so let's give them a name, if the attaching map maps, now I have to think, it maps 1 to this 0 cell, EJ, and
I think I used the convention that the characteristic maps get as upper index the dimension of the cell, so it should be index 1 and not index 0.
You're right, you're right. And here it's correct with the incidence number, yeah. So we need a 1 here. And I also want that Qi1 of -1. Remember, S0, the way we embed this into the real line is via the 2 points, -1 and 1. And this should be unequal to this 0 cell. It is -1 if this is EJ0 for -1, and I also want that for 1 it is not this 0 cell. When is it 0? Well, let's just write otherwise. So in particular in the situation where both endpoints map to the same 0 cell, then it's 0. So,
or if it's not hit at all. Yeah.
Exactly. So this would be situation. So what do we see here? What I symbolize here is the map from D1 and then let's say that point here is EJ0, 0 cell in the 0 skeleton. And if we are in that situation, then we are in the second case. So here we have incidence number -1. So that is the case where we have incidence number 1. And then we could have the situation like that, where this is EJ. Or we could have the situation that EJ is somewhere completely untouched. Could lie here, and here is the cell EJ0, and then in both cases this would be situation where we have incidence number 0. So now let's look at an example. The first example
Maybe just one comment before you start with the example is that just to keep in mind, this is not a new definition or so, yeah? So this is what should come out of the definitions and convention we have agreed upon.
Maybe it's good to write down again what happens in this degree 0 in the base case. Okay, and now you see it's a bit particular in this low degree because S minus 1 is the empty set. And the convention with taking quotient space by an empty set is this is just D0 with an additional base point.
And actually, not even this is a convention, right? If we define the collapse space by the push out via the additional point, then this is what comes out if you let out the empty set.
That's true. So this is S0. Therefore, this isomorphism that we had in higher degrees is also valid in this low degree. Didn't we have a name for this map?
Yes,
this
U naught now.
U naught, yeah. All right. Okay, and the map here is the one that maps this base point that comes from collapsing the empty set to 1. So maybe I indicate this in blue, just as a side remark. So everything works also in this kind of extremal case. And the fact is, and Holger just mentioned it, that if you now look at what is induced in H0 by this map, so H0 reduced, then this is just multiplication with that number.
Yeah. I mean, this map is a map from 2 points to 2 points, so not much can happen, right? Either you sort of map them identically, or you swap them, or you map both points to 1 point, or you map both points to another point. These are the 4 options, and what they induce in reduced homology is what's written up there.
And if they are not in this situation where you map both points to the same point, then you automatically have a homeomorphism.
Yes.
So it can only be +1 or -1. And now one has to sit down with a sharpened pencil and really check that the conventions that we have fit together and give you the statement above, that the incidence number has this concrete form. So that's something that I don't want to do now. Let's look at an example. So the first example, one of the easiest, is S1 with a specific CW structure, namely this one, where we have 1 0 cell and 1 1 cell. Now, these incidence numbers, as you can see again here from the presence of these attaching maps and the maps capital Qj, they depend on the choice of the pushout, and we stressed this several times. So the CW complex is given by the space with its filtration. What is the additional structure of the choice of the pushout? What does this mean? Well, for the 0 cells, for the unique 0 cell, there is not much to choose. There is only one map from a point to a point. But for the 1 skeleton in its pushout, there is a choice. So the 1 skeleton looks like this. We have here this point, which I just call PT. And this map just maps both points to this point. What else could happen? And then the pushout for the 1 skeleton. So let's write this as X because it might be confusing to see another S1 here. This is an interval, and we have to map it to this circle. You can do it, of course, in zillions of ways, but homotopically there are actually only 2 ways. So you either map it like that, or you map the interval in the other direction like that. So this map here, to be even more specific, right? So I indicate this map again with these arrows, meaning if I go from here over there, then the images of the points under this attaching maps go like that. Of course, I could map it also in the other direction. And I could map it also in many other ways. I could somehow do it, the maps become slower here, then becomes faster. But that doesn't change somehow. I mean, I could change the speed and therefore describe different maps, but with the same orientation, but they will all be homotopic. And because they're homotopic, they will induce somehow the same incidence numbers. So there are essentially two ways to choose this map. And these two ways are often referred to choosing orientation. But choosing orientation is really choosing this map. We have two cells, one 0 cell and one 1 cell. So here there are only zeros, and this is degree 0, the degree, let's indicate this by these little numbers here. That's the cellular chain complex. What is the differential? The differential is just 0. Why is it the case? Because we are in this situation that I had above here, where the 1 cell is mapped, both ends of the 1 cell are mapped to the same 0 cell. The homology of that complex is, if you only have 0 differentials, then the homology is the chain complex itself. Therefore, H0 is Z and H1 is Z, and all others are 0, which is something we already know for the circle. Let's keep this 1 skeleton, but add more cells. Now let's throw in a 2 cell that fills this hole. The end result is a CW structure for the 2 disk. And for the 1 skeleton, we just take what we had above. Okay? So the little arrow indicates that I have already chosen a push out for the 1 skeleton. Again, there's only 1 2 cell. So there are 2 ways to write X like that. I can attach the 2 cell either with the identity map here, but I can also take another homomorphism up there of degree -1. You indicate this by drawing it like that, but you could also take another attaching map and therefore get another push out and take the other orientation.
And actually, little q2 doesn't have to be a homomorphism, right? It would also be allowed to go forward, a little bit backwards. But these exhaust the choices.
Oh, wait, which one? This one, the q2? Yes. No, that should be a homomorphism. I mean, you cannot do anything, right? You want to get the D2 in the end. So I want to discuss in a second an example where this map is actually...
sorry, the push out is supposed to be D2. I was thinking that you were going through the possible ways of attaching.
Yeah.
Okay, no, okay.
No, yes. I want in the end D2. So
yeah, no, then
but I can choose, it has to be a homomorphism, but it can go the other way around.
Yes, yes.
And in a second, we'll look at an example where we don't pick a homomorphism here, but another map. Let's first draw the cellular chain complex without the differentials. Then we have a cell in the first 3 dimensions. And here I want to fill the information about the differentials. The situation, so from degree 1 to degree 0, that's something that we just did. And since the 1 skeleton looks the same as in example 1, this is 0, same result. So what's happening here? And now let's look at the incidence number, but let's really have a close look by going back to the definition. We go from S1 to the 1 skeleton minus, divided by x1 minus, there's only 1 cell. And then, all right. Okay, so let's look at this definition of our incidence number, at least once more. All right, so what is x1? x1 is the circle, and now I take out the open 1 cell. So I take out this open, well, it's everything I take out except this point. So what is written here is just 1 point, a single point. So I collapse a single point, which means I do nothing. And therefore, this is D1 as 0. The identification is via this map Q1. Here we have little q2. And now you see that if it is like in this picture, then we get here the identity on S1, and therefore the map induced in first homology is just the identity multiplication with 1, the incidence number is 1. So this is 1 or multiplication with 1 if you want. The cellular homology of that complex is something that we know. We know it's equal to the singular homology, and D2 is contractible, so there should be only something in H0 and everything else should vanish. And this is indeed the case because, well, H0 is like before. H1 is the kernel of that. The kernel is everything, but divided by the image. The image is also everything, therefore H0 is 0. And then for H2, you look at the kernel here, but the kernel is the kernel of an injective map, so this is also 0, and then we only have zeros. I want to modify this example now by doing something similar, but gluing in a 2-cell, not by a homomorphism, but by a map of a different, of a degree, let's say degree 2. Right, so the push out, let me write it down, is then following. So here I have this map. This is a space, and one skeleton will be S1. So this is the one skeleton, and then I glue onto this X1, onto this circle, I glue another 2 disk along a map which is actually the degree 2 covering map. What is the cellular chain complex here? It starts the same as before. The self map of S1 that we get is actually exactly the map that stands here. And this is a degree 2 map which induces on first homology multiplication with 2. So the space we get, or the cellular chain complex we get, looks like that. What is the homology? Easy to compute from that. So H1 is the kernel, is everything divided by 2c. So this is just finite group of order 2. And then this is an injective map, and then there are only zeros. And this is a map, or this is a space, I should say, that we very well know. It is the projective plane.
And it's also a nice example where one sees that coefficients matter, right? If your ring wasn't Z, but some ring of characteristic 2, then your differential from the second to the first cellular chain module would be 0. And thus suddenly we've got
that's a good point.
Second homology.
I want to look at this homology of that space with the 2 coefficients, and also this can be then computed from the cellular chain complex with these coefficients. And what does it mean to have these coefficients? It just means that we take this chain complex and tensor it over the integers with C mod 2. That guy here is this guy. If I tensor C over C with C mod 2, then I get 3 copies C mod 2. Well, 0 stays 0, but multiplication with 2 is the 0 map if you have mod 2 coefficients. So this induces a 0 map, and therefore the homology with these coefficients look like that. So with these coefficients, we have something in degree 2, unlike we had with C coefficients where the complex shows that there is no homology in degree 2. So let's look at the torus. And for the torus T2, I take the following CW structure. So we obtain the torus, as we did many times, by identifying opposite sides in a square. Yeah. Okay, so this is the identification. We already know that the torus is a CW complex with that indicated structure, so there's only one zero cell that you see in this picture. These are these points, and they all get identified. And there are two one cells. This one here, which is the same, gets identified with this one, and the other one is this. One skeleton must be and is S1H S1. And then the two skeleton, and therefore the whole space, is described by this push out. And now I want to compute the cellular chain complex of this CW structure. So we know the modules. In degree 0, we have one zero cell. In degree 1, we have two one cells. Therefore, C1, CW is C plus C, and then we have one two cell. So that's the chain complex. We have to compute the differentials now. What about this differential? This differential is easy because all the one cells leave and end at the same point. There is only one point. So whenever you have a CW structure with only one zero cell, then the first differential has to be 0. What about this now? For that we have to, or we should, look at the definition of the incidence map. Now we have two one cells, and I should give them now maybe names. So let's call that A and the other B. Here, let's look at A. And maybe here I also indicate this by writing A. And we only have one two cell, we don't need an index for the two cell. What is this map? Okay, so we start with the circle here, and then the one skeleton is a wedge of two circles. But the attaching map can be understood by this map here, where this map is just, well, the obvious homomorphism to this edgy circle. So this is not a filled-in square, this is just the edges of a square. And then this map is the map that identifies the edges in the way as we had in the torus. Right? And then the identification gives you a wedge of two circles. And the attaching map that we have here, so that space is this one, this is this one, this is the map Q2. And this map was exactly this map. So we go like that and then follow the projection following the identifications. Now that map is just the projection to one of the circles, namely the circle belonging to A, and the other is just collapsed to the point. And then, well, okay, then there are some fixed identifications of the circle with itself, but it already looks like a circle. So this map here is that map. Now, what is the degree of this map? So what is the induced map in homology, in first homology? So to describe the map, what I do is I go around the circle and look at the image points. Okay, that way I show you what the map is. So if I go around here like that, then let's say that point is mapped to here, And let's also say we're looking to case A. So if I start here, move around here, look at the image points, then I move here, move here, move here, and move here. For the Von skeleton, the choice of a push-out is indicated by arrows. Let's move around the circle like that, look at the image points. And then in that picture, starting here, I'm moving here in a first step. That means I'm moving Vons around that circle. So now I move, if I follow along here, we go down here, which means we wrap around Vons this circle. Then we're here, so we're again in that picture at that point. Then I go here, meaning I go around the first circle in the other direction. And then I'm here, and then I go up here, meaning that I wrap around the circle that way. Again, if I do a full turn on that circle and look at the image points, the movie I get is the following. Here, then I go here, then I go here, and then I go around here. That's the map. So now what's happening if I go further, projecting one of the circle, let's say the right-hand circle, to the point? What do I see in that picture here? What I see when I go around the circle once, then the movie I get is I go around like that, and then I wait, because then I'm moving through that circle, but that stays on that point. And then I'm going around in the other direction, so that direction. Okay, maybe once more, I go around once, then I just wait, and then I go around in the other direction. And that is the map from S1 to S1.
Then you wait again.
And then wait again, yeah. That is the map from S1 to S1. That is the incidence number of the unique 2 cell and the 1 cell A. That map of S1 is homotopic to the constant map. And therefore, the incidence number is 0, and the other cell is a completely symmetric situation. There, it's also 0, and we get that the complex is this. And if you now look at the homology, as I said, if you only have 0 differentials, the homology can be read directly off from the cellular chain complex. So what you see here is the cellular homology of the torus. So you have a C in degree 0, 2 copies in degree 1, and another C in degree 2. And other homology groups are 0. So that's the 2 torus.